Future distributed radio infrastructures hold promising potential for positioning and mapping, which can be leveraged for efficient beamforming and robust communication even under user mobility. We acquire synthetic aperture channel measurements in a realistic hallway scenario, where we subsequently measure the channels from a single antenna agent to 15 anchors, each equipped with an 8x8 antenna array.
We will consider the LULIS testbed, which is a prototype of the radio waves architecture designed to support a total of roughly 1000 antennas distributed into panels. Unfortunately, the full prototype is still under construction, but the current modules can still be used to obtain the latency information associated to the main sources of latency. So let us consider several of these modules connected to each other in a daisy chain topology. The motivation for considering a daisy chain topology is that it allows for full MIMO processing by simply aggregating and forwarding the corresponding baseband data, while no switching is required, meaning that we can significantly reduce the latency associated to sharing data between the modules. A complete schematic of the LULIS testbed would look something like this, where we have several panels of antennas, each one connected through radio frequency chains to the modules previously shown. To achieve full MIMO processing, we should estimate and share some information during the data phase as well as during the pilot phase. Each module will be in charge of computing this information in their local processors. Then, the data would be shared to other modules and aggregated along the way, following a simple aggregate and forward scheme suitable for the daisy chain topology. The final module would then have access to the aggregated data, which could be used to implement a beamforming scheme as maximum ratio combining, or an interference cancellation scheme as zero forcing. We should note that implementing zero forcing requires performing a matrix inverse to the aggregated data at a central processor, whereas for maximum ratio combining, the aggregated data can be directly used to extract the user information without any centralized MIMO processing.
Let me start by introducing the core setup of our experiment. The channel sounder we used integrates multiple components, including National Instruments Universal Software Radio Peripherals, RF switches, and a pair of rubidium clocks. By combining parallel RF transceiver chains and RF switches, this system can measure up to thousands of antenna combinations within tens of milliseconds. This ensures highly dynamic capabilities without significant compromise on performance. On the transmitter side, a single 3 dBi dipole antenna was employed. This omnidirectional antenna, operating from 3.5 to 8 GHz, was mounted on a robot that could move via remote control. On the receiver side, 8 panels were connected to the RF switches. Each panel, designed to operate within the 5 to 6 GHz frequency range, consists of 8 dual polarized patch antennas. To maintain synchronization between the transmitter and receiver, we utilized rubidium clocks, which provided a 1 pulse per second output signal and a 10 MHz reference clock. The measurements were conducted in 2 main areas, an office room and an adjacent corridor. On the receiver side, the 8 panels were divided into 4 groups, with each group acting as a contact service point, or CSP.
Tactile is a research testbed developed at KU Leuven, designed for exploring advanced technologies related to communication, positioning, sensing, and wireless power transfer. This platform is part of the effort to develop future wireless systems, such as 6G, which will integrate not only communication but also distributed sensing, deep edge computing, and federated learning. The testbed provides an environment for experimental research on hyperconnected spaces, enabling scientists to test and validate new wireless connectivity and sensing solutions. Tactile's infrastructure includes 140 interconnected tiles, which contain various sensors and processors, such as Raspberry Pi devices, allowing researchers to study acoustic, RF, and optical strategies. The system also supports advanced synchronization and power solutions, such as Power over Ethernet, making it a versatile tool for next-generation technology development. Each tile in the Tactile infrastructure consists of several key components designed to support distributed wireless power transfer. A Raspberry Pi 4 to do local computing, connected to the Tactile server for central processing. A software-defined radio each equipped with 2 antennas, giving a total of 280 antennas in the infrastructure.
Our simulator, Unity Sim, combines the enterprise of Lund University with the power of the Unity game engine, as reflected in its name. It stands out with 3 key attributes. First, advanced channel modeling. By integrating geometry-based stochastic channel models, GSCMs, and leveraging raycasting techniques, Unity Sim realistically captures the complexity of multipath propagation. Secondly, realistic 3D environments. Using the Unity game engine, we simulate dynamic urban and indoor scenarios with high fidelity, utilizing 3D models derived from point cloud data to replicate real-world conditions. Lastly, it champions efficiency and scalability. Thanks to GPU acceleration within Unity, Unity Sim offers exceptional computational efficiency, significantly outperforming traditional tools or competitors like Sienna. With these capabilities, Unity Sim provides a powerful and scalable platform for cutting-edge 6G network research, bringing unparalleled realism and flexibility to wireless network simulations. So let's have a look at what that looks like. So this video demonstrates the ability of Unity Sim to process point cloud data. So the scene you're seeing now is a scene that's been generated from a point cloud on an industrial site. Now, the purple dots along the walls are transmitters, and the yellow lines, they converge to a point that is the receiver. And you can see the balls of the spheres that are scattered throughout the room are the multipath components, and the yellow lines represent the line of sight path, and the other colors, the line colors, are then the higher order reflections.
As testbed for simulation and validation of realistic propagation conditions, we developed a ray tracing-based simulator. The simulator uses planar wall segments to describe arbitrary environment geometries. Using geometric ray tracing in combination with a mirror source model allows to capture spatial effects, for example, visibility of multipath components. The employed mirror source model allows to select the desired order of reflections at the cost of an increased computational complexity with increasing order of reflections. When simulating or analyzing propagation over large arrays, computing the component visibility accurately is important already for low-order mirror sources. Especially in complex environments that are targeted at realistic use cases, this is a key feature. Comparing measurements obtained with a large virtual array spanning roughly 2.5 by 1.5 meters shows the need to accurately account for spherical wave propagation. The animations visualize radio signals measured over a frequency range of 7 GHz over time, with light colors representing higher amplitudes.